points where students seem to have a problem for solving waves problem in case of judgment, figures, and also how to draw waves easily, especially for the reflection and the refraction diagrams and what do they actually mean, and also some important stuffs about the lens figures. There's lens figures can give you some problems, how to draw them easily. I'm going to give you some heads up for those, and also the mathematical calculation regarding the refractive index equation, how to handle it with ease, so that you are never getting a wrong answer. These are the stuffs that I'm gonna share today. And this video that I'm recording right now, this will be uploaded on the YouTube as a private video, and the link of that video would be shared within your messenger channel, so that whoever has the link can see it, but it would not be published as public because we are doing this class exclusively. কথা শোনা যাচ্ছে properly সবার কাছে?
জি স্যার।
Okay, so let's jump right in. তোমাদের কোনো কোশ্চেন থাকলে বা স্পেসিফিক কোনো টপিক পড়ার সময় করা হচ্ছে, ধরো আমি রিফ্র্যাকশন পড়াচ্ছি, জেনারেল ওয়েভস বা রিপল ট্যাঙ্কের রিফ্র্যাকশন পড়াচ্ছি, তোমার রিফ্র্যাকশন রিলেটেড কোনো কোশ্চেন আছে বা স্কুলে কোনো একটা কোশ্চেন দিয়েছিল যেটা তোমার ডিফিকাল্ট মনে হয়েছে, ইউ ক্যান অলওয়েজ শেয়ার দোজ আপ. সো ব্রিং দোজ আপ, ফিল ফ্রি টু শেয়ার ইয়োর প্রবলেম ইফ ইউ হ্যাভ এনি, which really helps. Alright. আচ্ছা, আমি কি লাইট থেকে শুরু করে ব্যাকওয়ার্ডস যাব নাকি একেবারে জেনারেল ওয়েভস রিপল ট্যাঙ্ক ওগুলা থেকে শুরু করব? হাউ ডু ইউ প্রেফার? মানে তোমাদের ঝামেলা হয় কিসে কিসে?
আচ্ছা, কি বললেন আবার বলবেন?
মানে আমি কি লাইট চ্যাপ্টারটা আগে করাই ফেলবো? কারণ টিপিক্যাল সিকোয়েন্সটা হচ্ছে যে প্রথমে আসে হচ্ছে জেনারেল ওয়েভস মানে হচ্ছে রিপল ট্যাঙ্ক, তারপর হচ্ছে বেসিক ভি ইকুয়ালস টু এফ ল্যামডার ফর্মুলা কিভাবে আসে, ডেফিনিশন গুলি, আর হচ্ছে ইলেক্ট্রোম্যাগনেটিক ওয়েভস এর ইউজ এর একটা হোল জিনিস আছে, ওটার একটা পিডিএফ আছে, ওটা তোমাদেরকে আমি ফরওয়ার্ড করে দিতে পারবো. জেনারেল ওয়েভস এন্ড ইএম ওয়েভস, দ্যাটস দ্য ওয়ার্কশিট নেম দ্যাট আই গিভ. আর হচ্ছে তারপর আছে হচ্ছে সাউন্ড, মানে ইন সিলাবাস ফর্মে. তারপর আছে হচ্ছে লাইট. এখন লাইটের মধ্যে আবার অনেকগুলো ভাগ আছে. প্রথমে একটা হচ্ছে বেসিক লাইটের বেসিক ডিসকাশন, রিফ্লেকশন, রিফ্র্যাকশন, ডায়াগ্রাম, ফর্মুলা, আর তারপরে বড় একটা পার্ট আছে হচ্ছে লেন্স নিয়ে. সো তোমাদের I can start from light and go backwards, or I can start from here and go downwards, however you feel like. তোমাদের স্কুলে যখন তোমরা লেকচার ফলো করছো, কোন চ্যাপ্টারটা ডিফিকাল্ট মনে হয়েছে বেশি? I would like to start from there.
স্যার, আমার লাইটের লেন্সের পার্টটাতে সবচেয়ে বেশি প্রবলেম হয়েছিল।
Okay, can give it a start. Anyone else? Yes, কে যেন বলতেছিলা?
Light is a problematic thing for me as well.
লাইট, আচ্ছা ঠিক আছে, আমি তোমাদেরকে লাইট থেকে বলবো, বাট ঠিক আছে, সমস্যা নেই. আমি এখান থেকে দুইটা বা তিনটা ডেফিনিশন একটু টাচ আপ করে যায়, কারণ ডেফিনিশন গুলা বোঝা একটু ইম্পর্টেন্ট. তোমরা বেসিক টাইম পিরিয়ড বুঝো. টাইম পিরিয়ডের বেসিক আইডিয়াটা হচ্ছে the amount of time an oscillating particle or a periodic particle, periodic is can be also applicable for time period. Oscillating না হলেও time period applicable. For example, একটা অবজেক্ট যদি সার্কুলার মোশনে ঘুরে এবং ইউনিফর্ম সার্কুলার মোশনের মেইনটেইন করতে থাকে, every single time it goes through a specific point over the circle, that can be considered as one time period. So it doesn't essentially have to be oscillation. Oscillation typically means back and forth motion in a linear pattern. So this is typically oscillation, back and forth. This is our equilibrium. Back and forth motion represents oscillation, but this is circular motion. Circular motion is not oscillation. Don't get me wrong. Time period is applicable for any periodic motion. But the way typical way we say that the amount of time it takes for one particle to complete one full oscillation is called time period. Now you have to understand very clearly how much motion do you understand as one full oscillation. One full oscillation means to move 4 times the amplitude. Now let me tell you what this is. Let's say this is the equilibrium level of for a certain particle. আমি এই জিনিসটা এখানে বলতেছি কারণ হচ্ছে আমার এখান থেকে v equals to f lambda derive করা লাগবে, যেটা পরবর্তীতে আমার লাইট চ্যাপ্টারে এসে লাগবে। So I'm gonna show you the derivation using this definition, and then I'm gonna directly jump into light. Sound মাঝখানে বাকি পড়ে থাকবে, সাউন্ডকে একটু পরে পিক আপ করবো। জাস্ট ডেফিনেশনটা বিল আপ করার জন্য আমি তোমাদেরকে ডেফিনেশন ইকুয়েশনটা বিল আপ করার জন্য আমি ডেফিনেশনগুলো নিয়ে একটু হাওয়া করতেছি, একটু খেয়াল করো। Let's say this is the equilibrium position for a certain particle, which means this is a resting position, this is the balance position. Equilibrium is the most common term that we say. It means if there is no disturbance in the medium, this particle is preferring to stay at this point. Let's say a transverse wave comes by, which is gonna give this particle a vertically upward and downward motion. Let's say this particle is going to go up and down by 4 divisions on this whiteboard scale. So when the wave is gonna go by, this particle is gonna go up and down like that. Now there are two type of graphs that this particle can give us. Whenever we are trying to draw graphs for waves, we can either draw displacement versus distance graph, which might as well look like this, a sine curve kind of shape. We might also have graphs of displacement versus time graph, which might also look like a sine curve. Now you have to understand this very, very clearly. Which graph means what? Displacement versus distance graph is basically the shape of the wave when seen from the side. The shape of the wave when seen from the side. Let me give you a very simple example. Let's say you have an aquarium, which is basically another crude version of a ripple tank. And if you dip something on the side, let's say you have a marshmallow with a stick over here, and you're dipping this over here, and you're producing a wave. This is how the wave is going to look like after a while, and this is going to be moving from left to right. So if you just see it from the side of the glass, the shape that you're going to see is this one. This is that displacement over distance. Physically here, the distance between from crest to crest or from trough to trough is what we define as one wavelength, because this is distance, so horizontal distance is given as one wavelength. And also the maximum displacement, important bit, the maximum displacement covered by any of the particle from the equilibrium position is named the amplitude. So this much is what we are calling the amplitude. This is given as typically given as capital A. So this is the basic overview of the medium itself, let's say in a way that it is frozen in time. So the wave was going through, we snapped a picture with a very high speed camera, so there is no blur, and we can see this shape of the medium, and from that shape of the medium we can pretty much measure the lambda, provided that we have a meter rule over here. We can take some measurements, and we can also take for the amplitude as well. This is the displacement versus distance graph. Whereas we can also have this graph sometimes. This is displacement versus time graph. Try to understand, they are not the same. They might appear similar in shape because they are actually similar in shape. This is what is happening. Let's say this is the medium on which the wave is passing by. If I place one small particle over here and concentrate on the motion of this particle, and as the wave is going by, this particle is going, let's say, up and down, up and down. And let's say I'm going to, with a high-speed camera, I'm going to record its instantaneous position. I mean displacement data. Where is this particle at 0 second? Where is this particle at 0.1 second? Where is this particle at 0.01, 0.2 second? Where is this particle at 0.3 second? I'm going to gather instantaneous position data of this particle, let's say for every 0.1 second, with a very high-speed camera. So what's going to happen? As the wave is going to go by, the particle is going to go up and down, up and down, up and down. And later I'll plot all of those data, displacement and time data, on a graph paper. This is a thing which is an artificially drawn graph. You do not see this directly from the wave source. This is a side view of the whole medium, but this is not. This is a time plotted graph. Kids, are you getting my point? This is a time plotted graph for a single particle as it is moving up and down. So let's say at 0.0 second it was 0 position, at 0.1 second it was at this position. Now at 0.2 second maybe it was at this position. This does not mean that the particle is moving to the right. This is simply the position of the particles at different time instances, but because time is plotted over here on a horizontal scale, that's why the displacement is slowly becoming on the right. The particle is still going only up and down. The particle is still going only up and down, but it is at different position at different time instances. So this is the displacement versus time graph. Here also, from this graph as well, we can also measure from crest to crest, but this crest to crest distance basically gives you the time period. What this essentially means, or trough to trough position also gives you time period. What this essentially means, the amount of time a particle takes to complete one full oscillation. This actually gives you a very clear idea for how much do we understand to be one full oscillation. Typically, from where we can see that, you can see if we observe from crest to crest, it means what? That the amount of time it takes for the particles to start from the very tip position and then drop all the way to the bottom and then all the way rise to the top once again. So if the particle is observed to be starting from here, if the particle goes all the way to its trough position and then rise all the way up back to its crest position, this amount of total movement is what we define as one full oscillation. Get this. If we start the observation of the particle from the crest, the amount of movement, that is, if the particle drops to the equilibrium, drops further to the trough, then rise up from the trough to the equilibrium, and then rise up from the equilibrium to the crest position once again. So it practically reaches the exact same point, and that's how we cover one full oscillation. So in this whole process, try to think about it. If this much is amplitude A, starting from here, going all the way down and going rising up all the way up, how much physical distance is covered, do you think? I wrote it over here somewhere. Do you see it? I'm going to show you the other examples as well, but in this entire movement, 4 distance is covered. এই সব বুঝাই গেছে কিনা বলবান?
জি স্যার।
ঠিক আছে, কোশ্চেন থাকলে আমাকে বলো. So this particle is going to cover 4A distance. It can be equally considered that if the particle starts from the very bottom, rises all the way up to the crest position, and eventually comes down all the way to the down, it's still going to cover 4A distance. What if for another for some other part? So that's a pretty important bit. The way we define one full oscillation, the definition of the one full oscillation goes like this. Whenever a particle reaches the same point of motion in its oscillation from the same direction, two things. Let me write those. Whenever an oscillating particle reaches same position, no, not position, same point of motion No, same point of motion can be a bit of a vague term because it doesn't actually give you a bit of an it doesn't give you an idea that what are we actually talking about. It could be so let's just write measurable information. Same point of motion actually makes sense, but for physics it's better you write some measurable definitive quantity. So I'm going to write it reaches the same displacement. Actually, I did not brush through the definition, so that's why I'm refining my definition with core understanding as I'm writing by, so that you can also understand that how you should judge a proper definition. Qualitative and quantitative definitions can vary in a lot. Same displacement, whenever an oscillating particle reaches the same displacement in its motion from same direction. Now let me clarify what this means. Let's say let's say this is the equilibrium level for a certain particle. Let's say this is the equilibrium level for a certain motion. Okay, we have a pretty large particle over here, and here this much length is one amplitude. We can choose to start to see the particles motion starting from the crest. In that case, the situation is pretty simple because the particles have momentarily zero velocity at the two ends, and as they move towards the equilibrium, they speed up and they cross to the equilibrium at maximum speed, and as they go away from the equilibrium, they slow down and reaches to zero velocity. That's basically how the oscillation is dictated. How this thing is relevant to time with time, this is a certain topic that that's saved for much later. For the time, you just have to understand this much, is that As the particle leaves away from the equilibrium, it slows down. As the particle approaches the equilibrium, it speeds up and it crosses the equilibrium position with the maximum speed. So this is how the motion of the particle happens. Now, important bit. If we start to observe it from here the velocity was practically zero. And there is only one position over here. So this particle is one full oscillation is very easily definable the whole way, going all the way down and all the way up. What if we start to observe the motion from the equilibrium? Let's say a particle was initially going downwards at t equals to 0, the motion was downwards, and the particle is going to go all the way down, and eventually it's going to start going up, and it's going to reach the equilibrium position as it is going up at some time frame. Let's say that time t equals to 1.0 second. At 1 second, it reaches this point. Now, should we call this much movement as one full oscillation? By definition, we should not. The definition says that the particle should reach the same displacement of its motion from the same direction. Try to understand, at t equals to 0, the particle was going down, but at t equals to 1 second, the particle is crossing the exact same point. In which direction? Up. So this is not one full oscillation. So we should observe the motion a bit more further. So if we allow the motion to continue further, the particle will rise all the way up. It reaches the peak crest, and then eventually it's gonna slowly fall down. And after some time, 1 second, it's gonna reach up to here. And let's say that happens at t equals to 2.0 second, when the particle is once again going down at the same position. So we're gonna say this is our time period. And this motion, when the particle reaches the same displacement from the same direction, is defined as one full oscillation. This basically gives us this three-way information. Have a look. আচ্ছা, এখানে তোমাদেরকে আমি আরেকটা জিনিস দেখাই। আচ্ছা, এই পার্টটা কি বুঝা গেছে যে এটা কিভাবে 2 সেকেন্ড হইলো? মানে the idea of the from the same direction, এই জিনিসটা টিপিক্যালি স্টুডেন্টদের কনফিউশন হয়. Do you understand this part clearly?
Yes, sir.
ঠিক আছে? আচ্ছা, যদি কোশ্চেন হয় আমাকে কোশ্চেন বলো। এটা যে আমাদেরকে আইদার সবসময় এই তিনটা পয়েন্ট থেকে জাজ করতে হবে যে আইদার ফ্রম দ্য ক্রেস্ট অর ফ্রম দ্য ট্রাফ অর ফ্রম দ্য ইকুইলিব্রিয়াম পজিশন, এরকম না। In applicable cases, not applicable for your level yet, you can also we can also choose to observe the particle at any random point. আমি যদি একটা পার্টিকুলার মোশন এখান থেকে জাজ করতে চাই, তাহলে আমার ফুল অসিলেশন মার্ক হবে এভাবে, this going up. Just to make sense, I'm drawing the next arrow on the side, going all the way down to the bottom like this, and then rising all the way up to that same level. So when the particle is going to reach up to this point, if the initial motion was going upwards, when the particle is going to reach that same point while going upwards, this much motion will be defined as one full oscillation, for which it will take also one full time period amount of time. So that's how what we mean by one full oscillation. One full oscillation means when an oscillating particle reaches the same displacement in its path or in its motion from the same direction, that amount of movement is defined as one full oscillation. The amount of time it takes for one full oscillation is defined as time period. এখন কথা হচ্ছে যে একটা ফুল টাইম অসিলেশনের মধ্যে, একটা ফুল টাইম পিরিয়ড ডিউরেশনের মধ্যে একটা ওয়েভ কতটুকু ডিস্টেন্স কভার করে? দ্যাট আনসার ইজ ল্যামডা। বাট হাউ ডাজ দ্য ওয়েভ কভার্স ওয়ান ফুল ল্যামডা ডিস্টেন্স in one time period amount of time? That's I'm gonna show you. কোন ভিডিওতে ইজি ভাবে লেখা যাবে? Actually v equals to f lambda proof animation. This might come in help. Not photoelectric effect. আচ্ছা আমি এত ঝামেলা না করে বরং প্রোগ্রেসিভ ওয়েভ একটা প্রোগ্রেসিভ ওয়েভ অ্যানিমেশন বের করি, তাহলেই তো ঝামেলা চুকে যায়। Spelling mistake, but okay. Okay. This is a mathematically generated video from MATLAB or Cisco, but yep. This is actually a tool which we can also find out in the other. If I went for, other than finding the animation, if I went for the what is this thing called? Uh, uh, simulation. Yeah, these are some mathematically designed simulation which we can find out. Now I'm not gonna run through the process to set up all these things, because this actually gives us a pretty beautiful, useful wave. So here's the thing that I want to all of you to show you. So this is a wave that is going by. Please have a look at this red circle over here. This red circle is going up and down, causing this bar to go up and down. These are mathematically related. Where does the circle come from? No, for the timing, I'm not discussing that. So okay, I'm not being able to pause it at the lowest point. Okay, now, so this is the trough position, and you can see from here to here we have one full oscillation. Now this is the part that I want you to see. Have a look. When the wave is gonna go by, at any position of the wave, from crest to crest or from trough to trough, we can define as one wavelength. I want all of you to see as this green particle, which is the closest one, goes all the way down and then goes all the way up. How much horizontal distance does this crest go to the right? Take a good look. Currently, this red dot is at the bottom of the circle, and this is one of the trough position. So I want to see how much this crest position moves to the right as this green dot makes one full oscillation. Have a look. This is something that is better understood while seen on a simulation or on an animation, other than I'm trying to telling you, or you could also take my word, but this actually makes understand better. So have a look. This green particle is going down, so it has started its oscillation, and the crest is also moving to the right. This shape is what we're calling the crest, and this green particle is what by which we're going to determine one full time period amount of time. So now the green particle is pretty much at the bottom, not exactly at the bottom, and the crest has moved a little bit to the right. And when the green particle is reaching to it's not. No, it's not. Oh man.
So that's kind of the skeleton of this proof, but maybe you found that sort of illustration or that logic
এত কিছু না করে আমি প্রথমে ফেটে আসলে ভালো হতো। Come on, browser, work. Do I have to download? Can I not play? All right. So fixed and we're damping none, and then tension high, oscillate. I would like it to slow, so tension high is better, and then loosened. All right, I want to take us. So let's go for slow motion. And is there a pause button here? Yes. Now we can see it very conveniently, because it's the actual simulation that they were using to go for it. All right. No, we wanted it to start from the peak. So this black button is not very much well pressed. Okay, now this is the crest position, and I want you to see as this particle goes all the way down and eventually it will rise all the way up. This crest position is going to move to here, representing that one time period. See this. When this particle is at the crest, let's say right now, then here is the crest position and the next crest is over here. By the time this particle will complete this entire one full oscillation going down and all the way up, this crest position is going to move to here. Have a look. You can actually use a bit of a ruler and also a bit of a timer. You see, this particle is going down and the crest is moving to the right. And this is half the time period because the particle just dropped to the most bottom position. And as it goes further high up, somewhere right exactly there, we have one full oscillation. And within this time, this crest position has moved to that position. And from one crest to the next crest is what we define as one full wavelength. The point that I'm trying to make over here is this. It's a very simple point, but this is what I want you to understand, that in t time, a wave covers lambda distance. Can we all agree on this statement? In t time, a wave covers lambda distance. Do you understand this thing, Pulaman?
Yes.
This particular has covered one full time period, and the wave has covered lambda distance in this distance. Now, this basically brings us to a three-part information which we're gonna use in unitary method, and eventually it will be done with v equals to f lambda. Sheta would say, here's the thing. This is how I prefer to write this. In t amount of time, any oscillating particle covers a total distance of 4a. I'm using the term distance because it covers a total 4a distance. And within this time, the wave covers a total of lambda distance linearly. I'm using arrows because these variables are not the same, but these are the amount of measurement which are related to each other. In t amount of time, the wave goes lambda distance. So it means if it is t by 2, the wave goes lambda by 2. If it is 2t, the wave goes 2 lambda. If it is 100 times t, the wave goes 100 lambda. In the same way, in a full time period amount of time, one oscillating particle covers a total distance of 4a, 4 times the amplitude. And it keeps having and it keeps happening that way. This is a very useful set of relationship that can help you a lot for mathematical questions for the upcoming parts. So if I just go for the v equals to f lambda, in t time the distance covered is lambda, so in unit time the distance covered is lambda by t. By definition, the distance covered in unit time is given as v, and we know from the definition of frequency that 1 upon time period can be written as frequency, so you can write lambda into f equals to v, or in other words v equals to f lambda. That's basically how the relationship v equals to f lambda came into existence, by the definition that in t amount of time the wave covers a distance of lambda, and ওখান থেকে ইউনিটারি মেথড করে আমাদের v equals to f lambda ডেফিনিশনটা ডিরাইভ হয়। এখানে আমি v equals to f lambda ডেফিনিশন আর দুটো জিনিস বলি, সেটা হচ্ছে you can see it very well, this is a tri-variable equation, right? v আছে, frequency f আছে, এবং wavelength lambda আছে. Now if you are trying to apply this equation for a variety of cases, in some scenarios one of the variables might have to consider as a constant, so that you can make a relationship with the other two variables. For example, কোন একটা certain scenario তুমি যদি v কে constant ধরো for two set of data, তাহলে আমরা লিখতে পারি যে v equals to f1 lambda 1 equals to v f2 lambda 2. সেই ক্ষেত্রে তুমি এই চারটা ভ্যারিয়েবল দিয়ে একটা ইকুয়েশন বানালে এখান থেকে ম্যাথস করে বের করলা। ইন আদার কেস তুমি যদি f কে কনস্ট্যান্ট ধরো, সেক্ষেত্রে তুমি হয়তো লিখতে পারো যে v1 equals to f into lambda 1 and v2 equals to f into lambda 2. So if you divide the whole two equations, you might actually get v1 by v2 equals to lambda 1 by lambda 2. সো ওখান থেকে তুমি দুইটা ইকুয়েশন, একটা ইকুয়েশন প্রপোর্শনাল ইকুয়েশন বের করলে, ওখান থেকে তুমি সার্টেন ম্যাথস করে একটা আউটপুট বের করলে, ইটস পসিবল। বাট ইউ হ্যাভ টু জাজ অ্যান্ড বি এবল টু চুজ কেয়ারফুলি দ্যাট হুইচ variable of this equation you need to consider as a constant, and depending on what scenario. Hear me out on this one. এক নম্বর জিনিস হচ্ছে, most important thing, once any wave, I'm saying the word any, it can be a mechanical wave which requires a medium to exist, or it can be a electromagnetic wave which doesn't require any medium to exist. But every wave requires a physical source, some matter from where it has to be created. You need some mass to create wave. So that's a very important thing. So there is a thing that is source, and there is a thing that is medium. Try to understand these two things differently. For example, whenever I'm talking to you, the way the sound is reaching to you, apart from the way my voice is reaching to the microphone, let me use that part, is that I'm controlling the tension in my vocal cord, and I have learned to speak in a certain manner. So I am vibrating my vocal cords in such a way that is vibrating the air particles, which in turn is taking the sound to the microphone. In this case, let's say the microphones are equivalent to your ears. You have to understand, my vocal cord is the source of the sound, and the air in this case is the medium for which the sound is required. The sound requires this medium to be transferred from my vocal cord to the microphone. These two things are not the same. Well, you might wonder, can air itself can be a source? Yes, in given other cases, it is possible that air itself can be a source. Sometimes air itself can be a source. It can be designed in that way. For example, if you think for flute, in the flute, we whenever or any type of air musical instrument, they actually blow into a pipe, some shaped or some length of pipe, and that makes sound. So in that case, air itself is the vibrating source, and air is also the medium or the carrier which brings the sound out and eventually make it to reach to up to our ears or the microphone. So you have to understand this two things clearly. That is, source is one thing, and the medium is a different thing. So mechanical waves are those which require a medium. Electromagnetic waves are those which do not require a medium. But every wave requires a certain source to be produced from. Now, whenever any wave is produced from its source, its frequency will be an unchanged parameter as long as that wave exists. Frequency is unchanged once a wave is produced. Which means, if you produce from a source if you make a wave that is of 100 hertz frequency, no matter what you do to this wave, you make it to go through different medium, you absorb it, or you do something, you make it reflect, you make it refract, you make it diffract, you make it to go polarization, you make it to go through a lot of optical phenomenon. No matter what you do, the frequency of that wave would always be 100 hertz, no matter what. This is a constant property of a wave which is exclusively dependent on the source. If the source produces the frequency at 101 hertz, the produced wave will be at 101 hertz, and that 101 hertz will be maintained. If the source produces a frequency of 1000 hertz, the produced wave will be at 1000 hertz, and as long as that wave exists, or as long as the energy of that wave exists within the medium, or maybe without the medium, it doesn't dissipate away, it will maintain a frequency of that hertz of the source, 1000 hertz. So it is exclusively dependent on the source, and once it is reduced from the source, that frequency will never be changed. This brings us to the information that whenever you are trying to consider one wave that is traveling from one medium to a second medium, you have to consider the frequency of this equation to be a constant. Simple example, let's say a light wave, let's say this is a medium where here is air and here is water. A light wave is about to enter from the air medium into the water medium. This is one single wave. So whenever it's going to travel from air into water, it is the same wave. So the physical property of this wave which will be maintained would be f. Because it is a different medium, so here the speed might be v air, and here the speed might be v water, and here the wavelength might as well be lambda air, and here the wavelength might as well be lambda water. So the way the equation is going to work, v in air, speed of the wave in air equals to frequency into lambda into air, and speed of the light wave in water, let's say vw, equals to frequency of the wave into lambda into water. In this case, the frequency would remain the same because we are talking about the same wave going through two different medium. And then if you're trying to do some calculation, you can very easily divide these two equations up, crossing out the frequencies. Then you have a 4 variable proportionality looking equation. You place the value of any three, you can find out the fourth one. It goes easily that way. এই পার্টটা কি বুঝা গেছে? পোলাপান
জি স্যার।
ফ্রিকোয়েন্সি পার্টটা কি বুঝা গেছে? যে একই ওয়েভকে নিয়ে যখন আমরা মাল্টিপল মিডিয়ামে জাজ করব, তখন তাদের ফ্রিকোয়েন্সিটাকে ফিক্স ধরতে হবে। সেক্ষেত্রে আমাদের ভি এবং ল্যামডাটা মিডিয়াম ডিপেন্ডেন্ট ভ্যারিয়েবল হবে। এটা হচ্ছে একটা সিনারিও, এবং এটা হচ্ছে তোমাদের সিলেবাসের ম্যাথমেটিক্যাল অ্যাপ্রোচেস এর মোস্ট কমন সিনারিও। লেটস সে ফর দিস কাইন্ড অফ ম্যাথ 80% of the math works in this manner. However, there are certain cases where the speed of the wave can be considered to be constant, and let me give an example of that. Speed of the wave can be considered to be constant. So if you want to consider this one as a constant, this is only possible for when your medium is constant. Now let me elaborate what do I mean by medium is constant. I'm going to elaborate this term for mechanical wave, or to be more exactly sound wave, and I'm going to elaborate this for EM waves as well. Acha. Pulman, I'm going to take a small 5 minutes break. Need to go somewhere. তোমরা তোমাদের স্কুলের লেকচারগুলো একটু উল্টা দেখো, that if you have any specific question of the waves that you would like me to ask, mark those paper or fold those papers so that you can ask me at any given time. I'm taking 5. So medium is constant is applicable for, I'll explain it for two different ways, for sound wave and also for the electromagnetic waves. Sound wave, whenever it travels through a specific medium, its speed is only dependent on temperature. It's a very important factor. So in air, at a fixed temperature, the speed of all sound wave is same. So at 0 degrees Celsius, regular air, I'm not going to say dry air, so regular atmospheric air, maybe some relative humidity is there. I'm not very sure about the relative humidity part, so I'm going to keep that variable constant. At 0 degrees Celsius, the speed of sound is about in air is nearly 336 meter per second. This is a 3SF value, so if you round it off to 2SF, it can be considered as 340 meter per second. So if you have sound of 100 hertz, if you have sound of 1 million hertz, 1 million hertz, irrespective, both of these sound waves through air would have this exact same speed. Which means if you consider in the formula v equals to f lambda, v is a constant. So if f is large, lambda has to be small. So high frequency sound would make very small wavelengths. Low frequency sound is going to make longer wavelengths. Not about the amplitude, it's about the spacing between crest to crest. That's the wavelength. Remember this thing. A source that is loud, a source that can make loud sound will have a longer amplitude. For example, big cymbal or a big drum where the source can move up and down by a lot, or for example a very large loudspeaker where the vibrating paper cone is very large, for example something that is used in the concerts, you can have a much louder sound. Loudness depends upon how much amplitude that sound carries, more or less, and frequency depends on how fast that source can vibrate. So if you are considering a sound wave in air at a fixed temperature, it will all sound waves in that temperature in air medium will have the exact same frequency. So they are all going to move exactly in this manner. This is also and depending upon the, so if you have a higher frequency, so if v is kept a constant, you can see from this equation, then if v is kept as a constant, then I can very well write that a constant equals to force, sorry, frequency into, I'm saying force, my bad, a constant is equal to force into lambda, which means the product of frequency and lambda has to be equal to that 340. So if you have a large frequency, you have a small lambda. If you have a small frequency, you have a large lambda, and vice versa. The product of these two things should always give you this number. So that's the scenario. Vice versa, if you have this for the electromagnetic waves, let's say in vacuum, all electromagnetic waves have the speed of 3 × 10 to the power 8 meter per second. It does not matter which part of the electromagnetic spectrum are we talking about. It does not matter which part of the electromagnetic spectrum we are talking about. You have to remember for your syllabus the whole sequence of the electromagnetic spectrum, which means this is the sequence. Here we have the visible light. Visible light, this is how I remember the sequence. Visible light goes like Vivgear. So I'm going to write Vivgear. Isaac Newton first did this divide, and he named 7 colors. Particularly, there are only 3 primary colors, but he considered it to be 7 colors, so we still learn it as the 7 colors for the rainbow: violet, indigo, blue, green, yellow, orange, red. Visible spectrum has these 7 colors. Above the visible spectrum, in terms of frequency, we have UV, and then we have X-ray, and then we have gamma rays. So these are the 4 levels. So this is one level, and this is the other 3 levels for the higher frequency part. And beneath the red we have infrared. So you can see that above violet we have ultraviolet. Ultra means more and infra means small. So beneath the red we have infrared. So we have, this is the another part of the intermediate spectrum. And then we have 2 parts of the wave. One is the microwave, and then we have radio wave. So we have 3 above visible spectrum, and we have 3 at the below visible spectrum. The way I usually remembered when I was a kid, for easier remembering, is that violeter upore hocche ultraviolet, which is very simple, and red niche hocche infrared. So I get these 2. And then if you look for this sequence going up, this is pretty much following the alphabetic order, that U, V, W is missing, X, Y. So X-ray is right after ultraviolet, and after X-ray we have Y. Gamma ray, the symbol for gamma is somewhat looks like Y. So that's how I used to remember. And on the lower side there was infrared. Right after infrared there was micro and radio. These 2 I sometimes messed up. Then I remembered that radio is the large thing and micro is the small thing. So micro comes on the bottom, on the top, and radio comes at the last. So these 2 I got a bit confused, but this is how I used to remember the whole sequence. So the electromagnetic spectrum is divided into 7 core parts in terms of frequency judgment. Here, this is very important. The entire electromagnetic spectrum is divided into 7 different segments depending upon its frequency. We have visible light, and a bit higher frequency ultraviolet range, a bit higher frequency X-ray range, a bit higher frequency gamma range, and frequency slightly lower than visible infrared, which is basically the heat waves. And then we have microwaves and we have radio waves. Different parts have different uses. We're going to talk about the uses after a while, no big deal. But what this tells us, that if any electromagnetic wave of any of this part, gamma, X-ray, ultraviolet, visible light, infrared, microwave, or radio wave, it is traveling through vacuum, all of these electromagnetic waves or any of these electromagnetic waves will have this exact speed, 3 into 10 to the power 8 meter per second, no matter which part of this electromagnetic spectrum it is from. Which means if it has gamma rays, it's going to have a very high frequency, it's going to have a very small wavelength. If it is a X-ray, it's going to have a bit more frequency, and it's going to have a bit less frequency, it's going to have a bit more wavelength. So you have to understand that this is the sequence where in this way the F is higher. So this is a higher frequency, this is the lower frequency. Whenever this light or any electromagnetic wave will travel from one medium to another medium, then things are going to be different. Let's say in water, the speed of electromagnetic wave is, let's say, something less than that. Let's say in water, that speed is, I'm just picking a random number, 2.5 into 10 to the power 8 meter per second. So I'm just reducing it by a small fraction. It would mean that any electromagnetic spectrum wave, if it is traveling through water, that speed would be 2.5 into 10 to the power 8 meter per second. If it is air, it is nearly equal to 10 to the 10 to the power 8 meter per second. For the case of waves, we consider the air and the vacuum to be pretty much equivalent medium. So that's not a big deal. But all of them would have the same thing. But once again, if it is gamma rays, it's going to have a very high frequency and very small wavelength, and so on and so forth. So if you consider the medium to be constant, in that case, you can consider the V to be constant. But if you consider one single wave, for example, let's say what's going to happen when a gamma ray, let's say here we have air, which is also equivalent to vacuum, and if it is water, let's say one gamma rays is going to enter from air medium into a water medium, is going to definitely refract. So I'm showing a little bit of direction change, and I'm going to talk about direction change in the refraction part after a while. No big deal. We have actually entered the light part. I hope you kids are understanding this part because I'm already drawing the reflection figures. So there is a smooth transition over here. If you have questions, ask me. So if we consider one specific type of wave, for example, if we consider one very specific gamma ray, then its frequency is constant because we have chosen one specific wave. Whenever one specific wave is going to go from one medium to another medium, in that case, for the equation, V goes to F lambda, F has to be kept as a constant. And if it is for any of the part in a one specific medium, then the speed has to be considered a constant. So one specific wave, frequency constant, one specific medium, speed constant. এই ইনফরমেশনটা মাথায় রাখা যাবে কিনা, বুঝা গেছে কিনা এই জিনিসটা? এটা আরেকটা রিপ্রেজেন্টেশন আছে রিপল ট্যাঙ্ক দিয়ে। রিপল ট্যাঙ্কের রিপ্রেজেন্টেশন আমি একটু পরে দেখাবো, বাট এই পর্যন্ত বুঝা গেছে কিনা?
জি স্যার।
Everyone else? Sami, Zain, Wasima?
Yes sir.
আচ্ছা, সো এইটা নিয়ে এই ভিকুস ডেভেলপমেন্ট ইকুয়েশন নিয়ে তোমাদের আরেকটা চ্যাপ্টার যে কোশ্চেন ফেস করতে হয় সেটা হচ্ছে রিপল ট্যাঙ্কের কোশ্চেন। আমি রিপল ট্যাঙ্কের একটা স্পেসিফিক কোশ্চেন তোমাদেরকে দেখাই। রিপল ট্যাঙ্কের কোশ্চেন একটা স্পেসিফিক পার্ট হচ্ছে যে whenever a certain ripple within the ripple tank, wave travels from deep to shallow or shallow to deep, because in case of ripple tank water medium, depth is the variable, depth of medium is the variable which changes the medium. It's the same material, it's still water, but the depth of water can significantly change how the waves behave. So to represent the variation of depth, I'm going to show you a ripple tank. Let's say this is a ripple tank which is filled up with water up to this much, and let's say underneath the water, somewhere over here, we have placed a piece of submerged block. So let's say this is a rectangular block we have placed at the bottom at the end. তার মানে হচ্ছে এই জিনিসটা যদি আমি টপ ভিউটা দেখাই, if I show you that this is the side view of the ripple tank, this is a glass tray, I'm assuming this is entirely filled up with water. If I show you the top view of this whole thing, this is the top view. Here we have water throughout this whole thing. Only in this part under the water, let me draw this. Oh, come on. এটা আচ্ছা ঠিক আছে, আমি যেহেতু রেক্ট্যাঙ্গল আঁকতে পারতেছি না, আমি এখানে একটা শেডেড এরিয়া দেখাইলাম। আই ওয়ান্ট ইউ টু কনসিডার that this is the border line. No, not triangle. আবার ওকে, এই পার্টটা বুঝে গেছে কিনা বলাবান, খেয়াল করো। So there is a submerged rectangular solid object. We can call it a glass block. Let's say this is a glass block that is submerged under the water. So because we are looking from the top, this is the part. So this is the part where the water depth is less. This is the part where the water is deeper. So this is deeper water. This is shallower water. The way it works is that if we place a bar to produce the ripples, let's say this is a bar. We're gonna use that's a black. This is the bar, and here the bar is represented as a cylinder on the surface, and now we're gonna start to move it up and down, and up and down motion cannot be drawn over here because it's a top view. Then the waves are going to be produced. The way these waves are going to be produced is that when the ripple time waves are going to travel in the deeper water, they are going to have a larger speed. So they're going to have larger wavelength. The moment they're going to enter into the shallower water, their wavelength is going to reduce because they're going to become slowed down. But important information, the amplitude would remain the same. What I want you to see very carefully, as I have drawn over here, I have tried my best to maintain the amplitude is exactly similar. Have a look. Do you see that? The waves are not losing their amplitude in any sense. And I intentionally did not draw it all the way at the bottom of this level, because drawing bottom of this level would practically make the waves hit the particle. Actually messed up over here. So this wave should go down a little bit. The amplitude of the wave would remain the same, only the waves are going to become more compressed. So here we have a larger wave lambda, and here we have a bit smaller lambda. But once again, this wave was produced from this one source, which means frequency is a constant property no matter where the wave goes. So in deeper water, we have bigger lambda. In shallower water, we have smaller lambda. Now, how can we sorry, I got a bit distracted. Sorry, I got a bit distracted. So how can we actually remember this thing? This is very simple. Have a look. The easier way to remember this thing. So I'm going to draw the waveforms over here after a while. But before I go for this thing, this is the easier way to remember. Have a look. Shallow means slow. I want you to remember this part. You can see that there's a lot of similar spelling. The alphabets are very common. Shallow water means slow wave, and other is other. Other means deeper water would give you what? Fast. Now, this would mean what? In shallow water, your speed is less. In faster water, your speed is more, because frequency is constant. So in the equation v equals to f lambda, faster means big speed and big lambda. Slower speed means small speed and small lambda. So that's how you can very easily remember. So whenever the wave is going to travel for the ripple time from a deeper water into a shallower water, it's going to slow down. It's going to slow down, and the way it's going to slow down is that it's going to have a significant reduction on its wavelength. How much reduction is it going to be? This is something that you don't have to understand for the physical factors. The question will provide you the necessary numerical data to be able to do some calculation. The most common type of calculation can look somewhat like this. Let me show you some example of this thing. This one, have a look. The refraction for the ripple time. Have a look at question number 1 maybe. The diagram shows a water wave in a ripple tank. The wave has a speed of 12 centimeter per second at r. The wave crosses a boundary PQ where the distance between the crest changes from 3 centimeter to 1.5 centimeter. What is the velocity of the wave at point S? So this represents the wave on the deeper water. This represents the wave on the shallower water. You can see that the wavelength has reduced by half. If because f is a constant, so you should remember that in the equation v equals to f lambda. Oops, where is that? In the equation v equals to f lambda, f is a constant, so I can pretty well write that v is proportional to lambda. So if higher speed would give us higher wavelength, and they should change in the same fraction. You can see over here that the wavelength got half, so the speed should also become half. Here the question gave us a speed of 12 centimeter per second, so here the new speed should be 6 centimeter per second. I can do this orally because I know how this math works, but if you are not confident about this, it's very simple. What you can do, you can see the given speed for the left part to be 3 centimeter, and the given speed for the left part is 12 centimeter at r. So this is the deeper medium. So you can calculate the frequency from these two information. V equals to f lambda. Have a look. This is v is 12, lambda is 3. So how much should be your frequency over here? Don't use calculator. Try to do it in orally. V equals to 12 equals to f into lambda. Lambda is 3. So 12 equals to f into 3. How much is f? Okay, I can write for you, since you are not responding. 12 equals to f into 3. So how much should be f? Anyone?
4.
F is 4 hertz. Beautiful. And that f4 should be exactly same over here. Now for the right part, you are asked to calculate the speed of the wave where the lambda is given. So you use the exact same formula once again, v equals to f lambda for the right part, but where if v is the unknown, and you replace the 4 from the earlier calculation. So 4 is over here, and from the diagram you can see very well that the lambda is 1.5. So if you place 1.5, 4 into 1.5 gives you 6. That's one way to do the math. The other way to do the math would be, because v equals to f lambda and f is a constant, so I can write that v1 by v2 equals to lambda 1 by lambda 2. Do you understand the derivation of this kind of proportionality equation? We have done this proportionality type of proportionality equations earlier, but do you understand how this comes into existence, Polaman? এটা কি বুঝো? এটা কনস্ট্যান্ট হলে কেন এটা হবে? I can show you. If you don't understand, I'll show you, no big deal. But if you do, then we'll not take time for that. I think I should show you. V equals to f lambda and f is a constant. That means that we can write this equation for multiple different v's and lambdas, keeping the f constant. So have a look. V1 equals to f into lambda 1. Because f is a constant, so f is not having a 1 or 2. In the same case, for a different medium, v2 can be written as f into lambda 2. Now, if I divide these two equations, what I'm going to get? V1 by v2 equals to f and f crosses out each other, lambda 1 by lambda 2. So if I use this equation, we can also go for this. So for the first medium, the speed was given as 12 centimeter per second. So I'm going to write 12 over here. I'm trying to calculate the speed for the second medium. So I'm going to write the unknown speed v2 over here. For the first medium, the wavelength is given as 3. Second medium is 1.5. So I'm going to write 3 over here and 1.5 over here. If you solve the math, here comes 2 and 2 crosses out as 6. We'll do the cross multiplication. v2 equals to 6 centimeters per second. So that's how you can also calculate. If you want to avoid all of this calculation, you can simply do this orally, that lambda became half, so speed should also become half. So 12 would become 6. That's the easiest way to go for, but it requires a certain amount of confidence to be able to choose that way. এই ম্যাথটা বুঝা গেছে সবার?
জি স্যার।
ঠিক আছে, এই সেম জিনিস এইরকম অনেকগুলো কোশ্চেন আছে। এই সেম কোশ্চেন এখানে রিপিট হয়েছে। নাম্বার 3 তে আমাদের এক্সাক্ট প্রপোর্শন নাই, বিকজ 1 meter got changed to 0.4. But the same thing, you can write the same equation, that v equals to f lambda for the deeper water, then for the shallower water you are trying to find the new speed, but the frequency remains the same. So considering the frequency is a constant, we can very easily go ahead and calculate this part as well. So this is how the ripple tank thing works for the v equals to f lambda equation. Any questions so far? Anyone?
No, sir.
আচ্ছা, এইটা গেল গাদা খানিক হাবি যাবি। সো তোমাদেরকে একটা জিনিস আমি এখনই দিয়ে দিই, পরে আমি ভুলে গেলে আর একটা বিপদ হবে। এইটা তোমাদেরকে ইয়াতে দিয়ে দিব, গ্রুপে দিয়ে দিই। আমি তোমাদেরকে একটা পিডিএফ দিতেছি, এই পিডিএফটা তোমরা এখান থেকে পড়তে পারো, বাট তোমাদের বুকলেটের সাথে এই পিডিএফটা ইনক্লুড করা থাকবে। বাট ফর দ্য টাইম বিং স্কুলের পরীক্ষার জন্য এটা এখান থেকে পড়তে পারো। দেয়ার আর কাপল অফ ইনফরমেশন ইন হিয়ার। Any of the part that if you don't understand, I have made them understandable, try to write them in easy words, but if you have any question, please do ask me. Okay, let me just show you what this PDF actually holds to give you a bit of an understanding. It actually has multiple couple of figures and how this thing actually does that thing. For example, gamma rays is for radiotherapy, sterilization, crystal spectrography to see the structure of various crystals and measure lattice spacing. Lattice spacing basically means to measure how far apart individual atoms are within a certain molecule. For example, chemistry তোমরা crystal structure বিভিন্ন রকম shape পড়ছো না. For example, you can have sodium chloride has cube structure, then diamond has tetrahedral, and so on and so forth. Did you come across this name in your chemistry? Did you yet come across these names? Maybe not. So different crystals can have different structures. So we can actually have this shape information by these gamma rays. Then we can have some industrial uses. This is actually a way to look inside a container that you wouldn't want to look by some person, because this can be a health hazard. Coals are coming in through a conveyor belt. You want to make sure that this whole container is filled up, but you don't want to overfill it. So the way it works is that when the whole container is empty, this conveyor belt delivers coal at a very high speed or maximum speed. The coal starts to fill up from the bottom. So there are two set of detectors over here. Whenever the detectors over here, whenever the coal fills up to this level, then a significant amount of gamma radiation will be absorbed by this coal material. So this detector will start to detect a low amount of radiation from coming from this source. So at that point, the automated control mechanism will slow down the conveyor belt, and when this will be filled up all the way up to this much, then this detector would be getting some low amount of radiation, because the coals would be blocking their path. They'll be absorbing a significant portion of the gamma radiation, and in that case the conveyor belt would stop, because that would be overfilling or we might have spill. So we have two radiation sources, two set of detector over here, one to slow down the conveyor belt, and the second one is to stop the conveyor belt altogether, so that we don't overfill it. So this is one other industrial use. So we can use the gamma rays to look inside. And one of the problem is given over here: excessive exposure can cause cancer and tumors. So I have given the uses and problems in two different type of bullets. X-rays have the also same problem: excessive exposure can cause cancer or tumor. Any type of high frequency stuff can give us problems. So UV can have some uses. This is a use how UV works with mercury vapor and everything. Visible light has, this is a view for the endoscopy device, that we send a light ray through optical fiber inside the body, because inside the body there is no light source. This light source goes up through this lens, then illuminates whatever the physical part inside the body that you want to see, and then light is reflected off that lens, and usually it comes back down through another tube to the doctor's eye. So you have to provide the light source, and you have to also have a way for that light to get back to your eye, so that you can actually see what you are trying to see. This is a very basic internal drawing for endoscopy device. This part is usually put inside the patient wherever we want to have a look. Then we can have infrareds. It's a view of an infrared camera. Hot objects are seen to be bright, and cold environment is seen to be dark. And then we have microwave, how microwaves can be used. The main use of microwaves is communication, not cooking. So and the uses over here are mentioned in terms of preferable order of weight as per CIE people. say examiners and say so whenever they ask for the what is the one of the most common use of infrared radiation, the most common answer that you're gonna see in your paper 2 or MCQ question is the remote control devices. Not all the remote controls that we use are uses a very low weak infrared signal, because infrared signals are basically heat signals, but they can be digitally coded as well for a small distance transmission. For example, within a room, if you're operating an AC or a TV, for that much distance, an infrared signal can be used, but it cannot be used for a very long distance. But then again, it's only a heat energy, so there is no possibility people are gonna get some hazardous effects like tumor or cancer or that kind of cell mutation problems from an infrared source. So it goes on like that. And here we have a figure for the ripple tank. So have a look at this. If you have any question about any of the uses, feel free to ask me on a later class. If I hope that happens pretty soon. So that's that. আর এখন আমি তোমাদের জিনিসটা দেখাবো, সেটা হচ্ছে যে লাইট চ্যাপ্টারের কিছু পার্ট। লেট মি স্পেসিফাই সাম প্রবলেম। তোমাদের একটা প্রবলেম হয় হচ্ছে ড্রয়িং এ, একটা পার্ট প্রবলেম হয় হচ্ছে mu equals to sin I by sin R equals to CA by CB এই ইকুয়েশনে। নিউটন না, তোমরা তো পড়া হচ্ছে n দিয়ে। দাঁড়াও, আরেকটা প্রবলেম হয় হচ্ছে total internal reflection relevant drawing এ। This is mostly MCQ question। আর আরেকটা প্রবলেম হয় হচ্ছে লেন্সেস এর ফিগারে। আমি একটা একটা করে দেখাচ্ছি। লাইট চ্যাপ্টারে ড্রয়িং এর ফার্স্ট পার্টটা আছে হচ্ছে ফর দ্য কেস অফ দ্য রিফ্লেকশন কেসেস। রিফ্লেকশন follows two rules. Number one, I equals to R. You know what these are. One important thing for you not to mess up, that optical angles are always created with the normal, not with the surface. The normal is always normal with the surface, not with any of the rays. So if you have a surface, intentionally I drew a curved surface. If you are trying to find out the reflection of light at this point, you have to draw a normal over at this point. So I have tried to draw a radius or something like that. And if a light ray comes in like this at this point, incident point, this is what we define as incident angle, not the other one. Optical angles are always created with the normal, not with the surface. This is very important. So first law of reflection is I equals to R, and the second law is that the incident ray, the reflected ray, and the normal, they all lie on the same plane. This actually requires a little bit of three-dimensional representation, because I cannot actually draw this on a 2D plane like this. এই পার্টটার এক্সপ্লেনেশন আমি তোমাদেরকে পরে দেখাবো কোনো সময়। এটা একটা থ্রি ডাইমেনশনাল একটা এক্সাম্পল লাগবে, বাট ফর দ্যাট টাইম ইউ ক্যান জাস্ট রিমেম্বার ইট দ্যাট the incident ray, normal and reflected ray, they all lie on the same plane. I equals to R is the very basic part. And এটা রিলেটেড যে ড্রয়িংটা আছে মোস্ট কমনলি পরীক্ষায় টিচাররা দেয়, সেই ড্রয়িংটা বের করতেছি। Not this one. Where is the new one? AJ. This is a very favorite question for the teachers, and they can give this to you. You need to know how to handle this kind of figures. These are not difficult, but you have to understand how they work. Have a look at question number 4. What does it say? Figure 4.1 and figure 4.2 are diagrams of a ripple tank being used to show two properties of waves. Figure 1a, figure 4.1 shows waveforms approaching a barrier in the water. So barrier in this case would essentially imply we're going to have reflection. Complete figure 4.1 to show the reflection of the wavefronts at the barrier. B, figure 4.2 shows the wavefronts approaching shallow water above a piece of glass. Complete figure 4.2 to show the wavefronts in the shallow water. This is actually a bit more easier, so I'm gonna talk to you about this one first. This is actually very simple figure. There is an intentionally I did not draw this figure over here because this is the question right over here. Do you guys understand what wavefronts are? Do you have a good idea for what are wavefronts? Well, one, try me. I mean, you can say anything, no big deal.
So I have the main problem in wavefronts.
Okay. Then I'll help. No big deal. Hear me out. Wavefronts are imaginary lines drawn through consecutive same phase particles to represent the shape of the wave. Wavefronts are imaginary lines drawn through consecutive same phase particles to represent the shape of the wave. Let me help you understand. Let's say this is the side view of the ripple tank that I was talking about. In the side view, you can very well see the shape. We have crest, we have troughs, we have equilibrium particles, we have so on and so. We have the whole shape available. These particles are all moving up and down, right? Because this is a transverse wave, so the motion of the particles is perpendicular to the direction of the wave or the direction of the energy of the wave. So wave is going from left to right, where the particles are moving up and down. Hence, it is a transverse wave because there's a 90-degree angle. Now, this happens to be the top view, which means whenever you are looking at this device from the top, this is the view that you are seeing. Now, these particles. So if I consider, let's say, the motion of this one, this vibrating bar, which is the producing the ripples. In this case, it's very easy to draw the up and down motion. How do you draw the up and down motion for alignment? You do understand that this bar is actually getting closer to you, and then it is getting farther away from you. But can you draw this easily on this figure? The into and out of motion, into the page, out of the page, into the page, out of the page. This motion can be proved to be pretty difficult for us to draw. This is equally applicable for when the wave is passing by. We cannot actually draw the motion of these particles, water particles over here, because showing them like this would be very wrong. Showing them like this would also be wrong because the particles are not moving in any of these orientations. The particles are moving into the page and out of the page. So if you're looking down, the particles are practically moving parallel to your line side, parallel to your viewing line. Do you understand the problem? That representing the motion of the particles is difficult for this orientation. But what if we still want to represent the wave from this orientation? How are we going to do this? That's basically where the wavefront comes in. So one of the ways that, let's say here we have a set of crest. It means I'm going to use the grid to roughly utilize it for my purpose. So let's say somewhere around this position, or maybe consider the very first line, we're going to have a crest. Now, this crest would mean, because this is a bar, which means this is actually disturbing a lot of particles side by side, and that would essentially ensure that the particles are all moving synchronously. This is important. The particles are all moving synchronously. Now, as this particle is at crest, then all of the neighboring particles would also be in crest because they're all were pushed by this particle at this bar at the same time, which means, yeah, I can draw over here a line representing a wavefront which represents all the particles which are. Do any of you know how to permanently stop this thing? Okay, I'm using smaller lines. Okay, this has to be one straight line, but because of the Microsoft Whiteboard getting smart, I couldn't draw a single straight line. But this means here all the particles are at crest position. I'm gonna draw the figure and it's gonna start making sense. That same thing can be available along this line as well. So if I use maybe this color, so from this point, if I this is I'm using the dotted line to give me a reference on the figure, but this dotted line doesn't actually mean any physical part. I can draw another set of wavefront that would go through the crests, all the crests of the particles along this line. This means whenever look from above, all of these particles are in their crest positions and all of these particles are also in their crest position. So definitely it would mean at the middle position, the particles are gonna be in their trough position. Typically for a wavefront figure, the troughs are not drawn. Typically troughs are not drawn. It doesn't mean the troughs are not there. Typically troughs are not drawn to avoid a lot of information or clumsiness or too much lines close to each other to avoid that. But troughs are always in between the crests. So just to make sense with you, I'm gonna draw the trough line over here with a bit of a dot line. So let's say here we have trough. Now, if you see over here, we are now basically representing the waves from a vertical point of view by some imaginary lines. If you ever try to find out these lines will never be found. These are just temporary lines that we've drawn to show the instantaneous position of a line of particles. This would mean all of these particles are in crest. So if you look from the side, these particles are in crest. So let's say this particle is at its crest, and then this particle is at trough. So if I draw, let's say this particle is at trough, and then this particle is once again at crest. So I'm gonna draw once again a crest like this. So I'm gonna pretty much get the same exact shape. As this bar is gonna go up and down, as this wave is gonna progress forward, this line, I mean this crest is represented by this line, this trough is represented by this dotted line, this crest is once again represented by this solid line, and we can actually have this continued further. So if I draw all the crests for the further on points, here we have another crest at this position. So let's say we're gonna have another crest right over here, and then we can have another crest right over here. So like this, and then we can have another crest right over here like this. So that's basically how it's working. What you want to understand, what you need to understand is that for the deeper water, this whole part represents the lambda, where for the side view, this whole distance represented the lambda. And when the water is traveling from the deeper water and for the altogether deeper water, this is also lambda. These two lambdas are exactly equal. These are for the deeper water lambda. So I'm going to write d over here. For the shallower water, the lambdas became smaller. So this much is lambda once again. So we are actually trying to represent the crest parts only to avoid confusion. But if we want to represent the troughs as well, we better use a different color or maybe a lighter shade, or better to use a dotted line to represent the uh, trough positions. So wavefronts are basically, I'm going through the definition once again. Wavefronts are basically imaginary lines drawn through consecutive same phase particles of the wave to represent the shape of the wave. So as the bar is gonna go up and down, these ripples are gonna move forward. So for example, you can let me show you another example in by animation. Okay. Let's use no. we not have a bar? Isolate obstacle. Acha, anyway, apparently we are not having a bar in this, but this is very, very. Oh, there it is. So you see, this is how refraction happens. So this is a very beautiful animation. Oh, this is nice. This is too good. Wow. So here we have a bit of a source. I can actually replace the source and I can realign the source to give me different alignments and orientation. So what I want you to see, can we get 3D view? Yes, beautiful. So we are producing some wave along this line. These waves, and this is a boundary layer. So here the reflection is actually happening at some angle. Let me just show you the reflection with the example that we are going through right now. Let's say I'm gonna make the source flat right now. Yeah, this is gonna work just fine. Stopped. So have a look. The waves are coming in. A little bit of part of the wave is reflecting back into the same medium, which is obviously going to happen. This is reflection. This is what we call partial reflection. A small fraction of the energy is reflecting back, and another fraction of the energy is entering into the second medium. When you can see it very well, all of these. Can I pause it? I apparently cannot pause it, but I'm going to talk through this anyway. So as you can see that these black and white lines, you see those gradient variation. Do you see that black and white lines? Alternate black and white lines. Where did this black and white line come from? I mean, does the water medium actually take a black and much whiter color as the wave travels through? That is a solid no. The water medium does not change color. Water remains transparent as is. Only some part of the medium are at crests and some part of the medium are at troughs. The lower points are typically represented by a darker color or a shaded color, and the higher points are the crests are typically represented by a solid color. So in this case, the black lines might as well be the crests and the blank lines might as well be the troughs, or it can be vice versa, alternate as well. It depends upon who makes the animation. But what they're trying to show you over here is that there is a difference of the individual spaces. There is a difference of the individual displacements. Here all of these particles on these bright lines, they are all on the same phase, they're all on crest, and the wave is passing through the particles, maintaining that crest position. So these lines are what we call the wave fronts, which is allowing us to see the shape of the wave from a vertical point of view, where the up and down motion cannot be drawn because the motion is currently happening into and out of the page for the surface. Do you get my point? এটা বুঝা গেছে কিনা?
জি স্যার।
মানে ক্লিয়ার হয়েছে? I hope so. Okay. So এখন এই জিনিসটা খেয়াল করো যে these waves are passing coming in, and whenever they enter into the denser medium, have a look, then the wavelength is becoming smaller and it is also moving slowly, but the frequency will always remain the same. And I'm not sure exactly how many waves we are creating over here. So if I show you the 3D view, so here the waves are being created, and as the wave is entering, you can see that they are really close. Actually 3D তে এখানে ভালো বোঝা যাচ্ছে না। আচ্ছা, সো আর যদি আমরা সোর্সটাকে একটু অ্যাঙ্গেল করে নেই, so let's say have a look. This is also another example of the refraction. Here we have the faster medium, here we have the slower medium. As the wave is entering into this medium, you can see that the wavelengths are becoming smaller. So here the wavelength is significantly smaller compared to this thing. And because of the significant smaller wavelength, you can see that the curvature is also changing. Here the curvature was much smaller, but here the curve is a much bigger. I mean, the radius of the curvature is much bigger. আমি যেটা দেখাচ্ছিলাম সেজন্য করেছিল refraction, sound duct, buffer position, hyper filter, scattering, rotating source. No. আচ্ছা, আচ্ছা এটা তোমাদের অ্যাকচুয়ালি লাগবে না এখন, এটা আরো পরে এএসএ গিয়ে লাগবে। আমি রিফ্রেশনের পার্টটাতে ফেরত যাই, রিফ্রেশনটা কোথায়? অলরাইট, এটা হচ্ছে এতক্ষণ তোমাদের দেখলাম হচ্ছে ভার্টিক্যাল রিফ্লেকশন। এখন তোমাদের বইয়ে একটা ঝামেলা আছে, যে বইয়ের একটা ঝামেলাটা হচ্ছে তোমাদের ফেডারেলের বইতে রিফ্লেকশনের যে ফিগারটা দেওয়া, সেই ফিগারটার সিচুয়েশনটা হচ্ছে এরকম। দেখাই, মনে করো এটা হচ্ছে রিপল ট্যাঙ্ক, এদিক থেকে আমাদের ওয়েভ আসতেছে, ইনকামিং ওয়েভগুলো এদিক থেকে আসতেছে, এখানে এটা দুই টুকরা করে দিবে, এবং এখানে ব্যারিয়ারটাকে রাখা হচ্ছে পারফেক্টলি 45 ডিগ্রি অ্যাঙ্গেলে রাখা, ব্যারিয়ারটা পারফেক্টলি 45 ডিগ্রি অ্যাঙ্গেলে রাখা। সো যেটা হয় যে রিফ্লেকশনের সময় ওয়েভগুলো এখানে বাড়ি খেয়ে পারফেক্টলি হরাইজন্টাল হয়ে উপরে হয়ে যাচ্ছে, বিকজ incident angle is 45 degree, reflection angle should also be 45 degree. So the reflected waves, these are the incoming waves and these are the reflected waves. This is only happening because the barrier was kept at a 45 degree angle. So this was 40 degree angle. With the duration of the incoming wave, the alignment of the barrier was 45 degree. That's why the reflected waves were going at 90 degree, because the incident angle, if I draw the normal over here, this is 45 degree, and the reflection angle, this is also 45 degree. Altogether you have a total 90 degree deflection. But that's not going to be happening every single time. This was an exclusive case, and because this figure is given in a federal figure, students in many cases think that reflection only happens at 90 degree. No, what you need to see over here, that for this figure the barrier is not kept at 90 degree. You can see that this is not a 45 degree barrier, this is a different angle barrier, so this is a bit more slanted than 45 degree. So the reflection is not going to happen vertically upwards, this is going to happen in a specific way, and I'm going to show you how to draw that very easily. But before I go into draw this one, do you all understand how to draw this figure? What should you, how do you have any idea? Can you propose some idea how could you draw this figure? Anyone? Okay, we're gonna try to draw this exact thing onto this figure. So have a look at the top before what is happening over here. In the deeper water, the media wavelengths are larger. In the shallower water, the wavelengths are smaller. So what are we gonna do? We're simply gonna draw, because there is no angle over here. The waves are entering at a perfectly same direction, so the change of direction will not happen over here. Only the gap between the waves are gonna become somewhat smaller. If this thing was at some angle, I mean, let's say if this piece of glass was not perfectly touching the incoming direction or the incoming wave fronts, then how would this look like? I'm going to show you this after a while, don't worry. But drawing this figure is actually very simple. All that you are expected to show in this figure is that as the water will travel from the deeper water into the shallower water, the wavelengths are going to become smaller, which basically means the wave fronts are going to get closer. So you simply have to draw at least 4 wave fronts. I'm saying at least 4 wave fronts onto the right, where the wave fronts should be parallel to each other and their gap should be less than the gap that is given over here. So you can very well pick up a ruler and hold your ruler against this line and give some equidistant closer dots over here. Just by measuring from a ruler, you can choose 0.5, 0.6, however you're comfortable, write at least 4 different dots, and do the same thing over here as well. This is the easiest way, in my opinion, to draw perfect parallel lines, and then carefully join these straight lines. If you want to fill up this whole thing, be my guest and you can do that. No big deal. It's not going to take too much long time, but it's not essential that you have to fill up the whole thing. Drawing at least 4 lines, parallel lines properly is usually good enough. এই ড্রয়িংটা কি বুঝা গেছে? এইটুকু আঁকলেই হবে এই ফিগারের জন্য। Bolaman, did you understand this drawing?
Yes, sir.
Parallel lines, closer lines. কার কোনো confusion? Anyone? Zain, Sami, Wasima? Maybe not. আচ্ছা, এইখানে রিফ্লেকশনের পার্টটাতে আমরা কি আছে, আমি রিফ্লেকশনটাতে ঢোকার আগে আমি এই জিনিসটাকে শেষ করি। সেটা হচ্ছে যে হোয়াট ইফ দিস পিস অফ গ্লাস ওয়াজ অ্যাট সাম অ্যাঙ্গেল। or this piece of glass was at some angle. So I'm going to show you once again back to the animation. Try to understand that this animation. For the time being, okay, just see and understand. Check this out. Disregard the reflection that is happening over at this part. You don't have to bother for the reflection at this point. Reflection will come in A2. But for the time being, just try to see the incoming wave and then try to see the refracted wave that is entering. So the wave is entering, and it is entering in such a way. Have a look. These black lines will remain black lines over here. They're only going to get closer. I do see that these same black lines are entering into the medium, remaining the exact same black lines, but only they are getting closer. Have a look. And the white lines as well. It is as if they are getting compressed. Do you see it, everyone? It is as if this wave, as it is entering, is actually getting somewhat compressed and also having a significant direction change. Here the direction was in this alignment. Here the direction change is this way. This guy is good, made some amazing animation. All right, so wow, hold up. Wow. Achha, never mind. I don't want to do these stuffs. How can I remove all these things? Delete. Okay. Clear waves. All right. Okay. So we can do a lot of stuff over here. Anyway, what I want you to see is that when the incoming waves are coming at some angle, in that case, they are having this bend. This is a question that is given in another of the year question, which we can find much later into the worksheet, which is, I think, in the, either in the composite or this one. I'll take this picture out. Select how. Okay. I want all of you to understand what is happening over here. Have a look at this question. Ripple tanks may be used to produce plain water waves. Draw a label diagram of a ripple tank used to produce water waves. You should draw, in your diagram, you should draw how the waves are made and how they are observed. Now, actual full-scale diagram of ripple tanks are really old questions. In your current version of the syllabus, ripple tank full figure drawing, a full ripple tank hasn't been seen in a very long time. So I would not very strongly recommend or strongly urge that you should learn this. But if you can learn this, well, it's a very good thing. but at least you should know the different parts. I mean, if a ripple tank is already given to you, you should be able to label the parts. That's very important. But also, if you can draw a ripple tank, I actually on the uses of the EM Waves PDF at the end page, I have given a very simple 3D diagram of the ripple tank. If you're trying to draw a ripple tank, the only way to draw it is in the 3D version. You cannot draw a ripple tank in a 2D version, because 2D version, so you cannot accommodate all the parts. There are three different layers. There is a light source, there's a ripple tank, and at bottom of that you have the white piece of paper, and you have to be able to label all the parts. So you have to draw a 3D diagram. Try to do this as best as you can. Diagrams in physics are not expected to be beautiful. They are expected to be understandable and distinguishable. So if you use ruler and sharp pencils and some time and some practice, all of you can get full score mark scoring diagrams. Diagrams are not supposed to be beautiful, so it's very important. They are just supposed to be understandable. আচ্ছা, এই জিনিস আমি একটু তোমাদের বোঝাচ্ছি। নাম্বার বি নাম্বারটা খেয়াল করো। Water waves may be refracted at a boundary. Figure 11.1 shows 4 wavefronts of water wave incident on boundary. এই কোশ্চেনটা বুঝো। কোশ্চেনে কিন্তু আমাদের মিডিয়াম টিডিয়াম কিছু বলে দেওয়া নাই। So this is a open ended question, so I'm going to help you to solve this to full scale. Figure 11.1 shows 4 wavefronts of a water wave incident on a boundary. As the wave crosses the boundary, the wave is refracted. So what we need to understand, this is a medium, on the right side we have another medium. The question doesn't say us which is fast, which is slow. Copy figure 11.1 and draw the wavefronts after refraction to the right of the boundary. So here they are asking you to draw it, copy figure 11.1, because it's an old question. So here they give all the questions in a single space, and then they have blank space on the end. But in your actual question format currently, you're never going to have to do this. So what they're asking us to complete the figure. To complete the figure. Now here's the deal. I would like to zoom in. These waves are approaching this boundary. And you have to understand one thing: wavefronts are always going in the direction of the wave. In other words, actually what I was trying to say, that if wavefronts are like this, the direction of the wave should be like this or like this, so that there is always a 90 degree between them. If wavefronts are like these, the direction of the wave should be like this, like radially outward, so that you always have 90 degree between them. My point: the direction of the wave and the wavefront, they always maintain a perfect 90 degree between them. So these wavefronts are approaching this boundary. So what should be the direction of these waves? In this direction or in this direction? To the upward right or to the downward left? Which one do you think? If these wavefronts are approaching the boundary. Let me make it easier for you. There is a boundary over here. So let's say there is medium X, there is medium Y. We do not know which one is faster or slower. Some waves are coming in from medium X and falling onto the boundary. So what is the most likely location for this source to be? Should the source be somewhere over here, spitting out waves in this direction? Or should the source be somewhere over here, spitting out wave in this direction? See if that helps. These 4 wavefronts were produced from a certain source. Where should that source be located? Behind these wavefronts, or in front of these wavefronts? Anyone? You are allowed to be mistaken. Please just try to respond. I'll help. Is anyone even here? Hello? হ্যালো, বলো, আমার কথা শোনা যাচ্ছে?
জি স্যার, শোনা যাচ্ছে।
আচ্ছা, আমার কোশ্চেনটা কি বুঝছো? What I'm asking you is that these wavefronts are approaching this boundary. So what do you think the direction of the waves are? Are they moving from left to right, or they're moving from right to left? That's my question.
Left to right.
Yes, that's the correct response. Do all of you agree with her, with Zareen, that these wavefronts are moving from left to right because they're approaching the boundary. এটি বুঝতেছো? This is obvious. আচ্ছা, so এটা কেন বললাম, এটা দেখাচ্ছি আমি। As these wavefronts are going to go through the boundary, eventually they're going to go into this medium. এখন তোমাদেরকে এইটা দেখানোর আগে, because this is a bit abstract, let me show you two different scenarios. So let's say মনে করো এটা হচ্ছে একটা রিপল ট্যাঙ্ক, ঠিক আছে? I'm showing a horizontal ripple tank. এখান থেকে মনে করো আমাদের এই যে আবার এখান থেকে মনে করো আমাদের ইনকামিং ওয়েভস গুলো আসতেছে। এখন মনে করো আমরা এই রিপল ট্যাঙ্কের এইখানে একটা ট্রাপিজিয়াম শেপের গ্লাস ব্লক ঢুকায় রাখছি। We have submerged a glass block which is trapezium shaped, let's say like this. So this is the shallower water. Sami, বুঝতেছো? Hello, Sami, are you here? আচ্ছা মনে হয় টেবিলে নাই, AFK. আচ্ছা, anyway, let's say we have submerged over here, other than a rectangular piece of glass block, we had a rectangular piece of glass block over here in the earlier question. This one was a rectangular glass block, and this face was perfectly parallel with the incoming wave fronts, or this face was perfectly perpendicular to the incoming wave direction. So these waves were coming in this direction, and this face is 90 degree with this direction. So we only had the reduction of wavelength. But let's say in another case, this is the scenario, and as these wavefronts are going to eventually incident onto this as these wavefronts are going to eventually incident onto this boundary, as they're going to shift from this boundary to this boundary, how are they going to change shape into this new boundary? That's my question. Do you understand my point? This is exactly what I want you to see in this animation. Let me show you the animation so that it is easier for you. I cannot make it an angle. Why can I not make it an angle? Acha, I'm gonna delete this medium and clear the waves, and I'll add a prism. I would like the prism rotate, oh yes, beautiful. Now I can please get selected. Okay, the reason I'm taking so much time with this animation, because this can really help you to understand how this thing happens dynamically within the medium. So you might feel a little bit bored. I'm not sure if you're actually feeling a little bit bored, but this will actually help you to understand. I'm going to make this source now vertical for the example that we are doing. So I'm going to recreate the exact thing that we are doing. Okay, clear waves. Now have a look. Do you see how the waves are going to change direction? Now we are having all those internal reflections because this is a closed medium. But for that, I mean, just forget about the reflections that are happening. Try to see the incoming wave and this refracted wave. That's the part that you have to handle for your syllabus. The wave is coming in, and here it is producing the reflections. And that is also getting reflected off this wall and is producing an equally opposite reflection, which is eventually getting dropped over here. And as these reflections are going out of the medium, they are also getting released into the green medium once again. And you can see there are some waves produced over here. So That can also happen. Could I make this all the way up in the screen? I think I could. Would that make it any easier? Bam. Nice. Better. So the waves are going to bend in this way. So আমরা এখন যে কাজটা করব, what I want you to see once again, I cannot pause this. I hope I could pause this. Is there a way to pause this? Simulation speed আচ্ছা 0 দিয়ে দিলে হবে। আচ্ছা হ্যাঁ, 1 this is simulation speed. Clear waves. Start once again. A bit more. And then as we are about to collide, একটা জিনিস খেয়াল করো বলবান, you can see that this black line is continued as a black line over here. Do you see that? This black line is continued as a black line. White line is continued as a white line. You have the same alternation of black and white lines, and then it is entering into the medium. So this alignment of the wave is changing into this alignment. So basically, this is the second wave that was created, and this is the earlier wave refraction. So do you see the difference? You have the same number of wavefronts, but only they are getting closer, and they are all parallel to each other, which means here the wavelength is less, here the wavelength is more. This is basically what we are trying to achieve for this figure. So what I'm going to show you for this figure to draw is that as these wavefronts, let me just now draw solid lines. Let's say this is the one of the incoming wavefronts. This is another incoming wavefront. This is another incoming wavefront. So let's say the question has given us this whole figure, and they're asking us to draw the continuation of these wavefronts on the right. How are we going to draw this? এই হ্যাশ লাইনগুলো কিন্তু ওয়েভফ্রন্ট না, এই হ্যাশ লাইনগুলো দিয়েছি শুধুমাত্র গ্লাস ব্লকটার প্রেজেন্স দেখানোর জন্য। এটা কি বুঝতেছো সবাই? There is a trapezium glass block over here. To represent the presence of the trapezium glass block, I've shown you these hash lines. Now, as these waves are going to enter into the shallower medium, they are going to get closer. So this is one of your incident point for this wavefront. This is one of your incident point from this wavefront. This is one of your incident point from this wavefront. As these waves are going to get closer, your only logical option is to make them bend like this. হলো না কেন? So I have drawn over here only 3 because I had 3 of the given wavefronts falling onto the surface. But once you have 3, you can very easily measure from them how much is the in-between space, and using a ruler, you can actually continue to draw multiple other lines, multiple other wavefronts as well. But you have to make sure that Microsoft Whiteboard is not making such troubles. Okay, but you have to make sure that they are all parallel to each other and they are all equidistant. So it's not essentially required for you. You don't have to actually know how much amount of bend you have to show you. All that you are expected to understand that as the wave will travel from a deeper to a shallower medium, the wavefronts are gonna get closer. So here the gap was large and here the gap is small, and that's why the change of the alignment did happen. এই ড্রয়িংটাকে বোঝা গেছে? The mark scoring point from this the mark scoring key point, the locations where you're gonna get the mark is that to be able to draw at least 4 lines on the right side which are parallel, equidistant, and that distance between these lines should be visibly smaller than the incoming wavefronts. এই 3টা পয়েন্টের উপর তোমাদেরকে এই ফিগারে মার্কস দিবে। You have to draw 4 lines at least which should be parallel visibly. They should be equidistant. Equidistant means এই দুটো লাইনের মাঝখানে যে গ্যাপ থাকবে, এই দুটো লাইনের মধ্যে সেই গ্যাপ থাকবে, এই দুটো লাইনের মধ্যে সেই গ্যাপ থাকবে। That's what we mean by equidistant. And also the gap amount should be visibly smaller than the incoming wavefront's gap. That's how the reflection figures are drawn. এটার একটা এক্সাম্পল তোমাদেরকে দেখাই। একটু আগে আমরা যে এমসিকিউটা করছিলাম সেই এমসিকিউতে এটার একটা ভালো এক্সাম্পল ছিল। এই যে দেখো, check out this figure. I'm gonna put it over here to make it a bit of a zoom in. See if this figure makes sense now. If you have any question, please ask me. This is why you are supposed to ask me questions about reflection diagrams. Anyone? আর বুঝা গেলে বলো, then we can move on to the next thing. I can try to show you the reflection diagrams.
জি স্যার বুঝেছি।
কোনো question? Anyone?
নো স্যার।
আচ্ছা, মানে কি কি পয়েন্টে তোমাদেরকে জাজ করা হবে সেটা কি বুঝছো? যে how are you supposed to draw this figure? I mean, it might be a bit confusing for you to draw the first line, but it is not actually confusing. What you are only expected to do, for example, মনে করো এখানে তোমার এই তিনটা লাইন দেওয়া আছে, তোমাকে এই চারটা লাইন আঁকতে হবে, ঠিক আছে? তো এই চারটা লাইন দেওয়া আছে, তোমাকে এই চারটা লাইন আঁকতে হবে। What you simply do, choose any of the incoming wave front. I mean, hold up your ruler like this. I mean, put your pencil over here, then choose a different angle than the incoming wave. So let's say that hold up your ruler like this and draw this wavefront all the way down. Then move your ruler as parallel as you can and hold up at this point and try to measure how much is this and try to draw a parallel line exactly from here over here. Do not draw this. I'm just trying to show you that you are supposed to measure this distance. So I'm going to erase this off. So you do the same thing from here and do the same thing over here and do the same thing over here. Drawing the first line with your arbitrary choice of angle is the key step. That you choose any of the incident point of the wavefront onto the surface, draw an arbitrary line that represents the bending, and then continue that parallel line drawing with all the other incident points. And that's basically it. আমি বোর্ডে হলে আরো হয়তো ভালো করে এঁকে দেখাইতে পারতাম, but that's I think the maximum I can do for the timing on a whiteboard and digital class. All right. As for the reflection diagrams that we have over here, there are multiple different ways we can go by, but there is a very simple thing that we can do. আমি সিম্পল জিনিসটা আগে তোমাদেরকে বুঝাচ্ছি যাতে করে তোমাদের আঁকতে সুবিধা হয়। একটা জিনিস খেয়াল করো পোলাপান, মনে করো এটা একটা সারফেস, লেটস সে দিস ইজ আ সারফেস। কি হলো? Let's say this is a surface. It's going to be a bit geometry, so please keep your eyes peeled. And if you are tired that you cannot take the lecture anymore, just let me know. I don't want to overstress you. It's been nearly 2 hours, so we can schedule another class tomorrow maybe. Let's say this is a normal. এখন let's say a wave, it can be a ripple tank wave, it can be a sound wave, it can be a light wave, doesn't matter. A wave is coming to this point at this angle. I'm intentionally drawing it not to be 45 degree. So we're going to call this is the incident angle. That's one thing. Before I draw the reflected wave, let me just draw the wave fronts of these waves. Let's say for this medium, for this given scenario, these are the wave fronts of these waves. I have to draw perpendicular, so I'm trying to choose a equal random distance to represent as the wavelength. It is too বড় হয়ে গেছে, but anyway, let's say these are the wave fronts. So as the wave is coming in, this entire shape is coming in. If I continue these waves over here and make them fall over here, ultimately এই ওয়েভগুলো কি হবে, এই সারফেস থেকে বাউন্স অফ করে উল্টা দিকে রিফ্লেক্ট ব্যাক করবে। Take a good look. This is a 90-degree angle, right? This is I. How much should this be? এটা 90 মাইনাস I হওয়ার কথা না? দেখতেছো?
Yes, sir.
তাহলে টেকনিক্যালি এই অ্যাঙ্গেলটা কত হবে? হ্যাভ লুক at this triangle. Check out for this triangle where this is a 90 degree, this is a 90 degree. How much should this angle be? I'll help you. This plus this makes 90 degree. This plus this makes also 90 degree because the total angle of the triangle is 180 degree. So shouldn't this angle be also I? খেয়াল করো। সিমিলারলি এই অ্যাঙ্গেলটাও কি হবে? আই। এই অ্যাঙ্গেলটাও কি হবে? আই। হবে কিনা?
Yes, sir.
এই জিওমেট্রিটা কি সবাই দেখতেছো? মানে দেখে বোঝা যাচ্ছে কিনা? It's the idea of complementary angles. Why am I showing you this? What I want you to understand in your heart is that the incident angle basically, which is the angle between the wave angle normal. This happens to be exactly same as wavefront angle surface. এই দুটো angle perfectly equal. Can you agree on this? The angle between the wave and the normal, which is the incident angle, and the angle between the wavefront and the surface, which is also the incident angle, they are gonna be always equal. Now, can I দেখাচ্ছি তোমাদেরকে? Here is the deal. When this wave is gonna get reflected off, let's say it's reflected off in this direction, where I equals to R, I equals to R. It's basically the same angle. This wave will also produce its own, which also should also have its own wavefront. So if I draw this individual wavefront, I'm not showing the wavefronts of this one, but if I just try to show you these wavefronts should be of equal spacing because the same medium, but I couldn't draw it equal spacing. I should actually rub this off. Try to draw it to be of equal spacing. So if I draw these, if I continue these wavefronts to the surface, if this angle is R, shouldn't these angles be also R? এদিকে বুঝতেছো বলবান?
Yes, sir.
That's basically how we're going to draw this figure. So what I'm trying to show you is that when the waves are gonna fall in, let me just show you a bit of reflection over here. Do we have basic reflection? Half lens? Actually, এখানে actually reflection দেখানো একটু difficult. Ripple tank simulation. এখানে তোমাদের রিফ্লেকশন আমি কিভাবে দেখাবো? আচ্ছা, actually can let me just get rid of this thing. I don't want this. সিলেক্ট করতে পারছি না কেন? Delete. Okay. Let's say the source is gonna be like this, and I'm gonna have add a barrier. Where is the barrier? Okay. And then the source is right here. Okay, clear waves. Start. খেয়াল করো try to see this one. Take a good look. The wave is getting reflected off. You cannot see the reflected off very well because it is actually overlapped with this incoming wave. Now that is a reflection. If I reduce this, you should see that it's picking an equal angle. Now this is almost 45 degrees, so you can have a bit of a hard time to see this. But if I just make it a bit more slanted, where the damping is okay, source frequency is also okay, clear wave. Now have a look. This is the incident wave. These are the wavefronts which are coming in. So I do not have a way to draw a normal over here. But imagine there is a normal over here. We can see a bit of a problem thing. And then the wave is reflected off from this boundary. But as it is reflected off, it is actually overlapping onto its original wave. That's why we had this zigzag shape. But ultimately, this is the incoming direction and that is the leaving direction. We should have another wave from here right now so that we can actually compare them. So you can see that this is the incoming wave and this is a reflected wave. So they are making equal angle on both sides. Why am I showing you this? Because whenever we are trying to draw this figure, we can very easily simply draw opposite wavefronts to complete this figure. What I'm trying to show you, when this ripple, this wavefront is going to incident onto this surface at this point, is going to produce a reflection so that the wave is going to go in this direction. Wave is going to go in the upward right. So the produced ripple or the reflected wavefront is going to look somewhat like this. This one's reflected wavefront is going to look somewhat like this. This one's reflected wavefront is going to look somewhat like this. These are going to be the reflected wavefronts, so that the duration of this wave is going to be this, which should be perpendicular to this red line, but I couldn't draw it to be perpendicular. The point that I'm trying to show you, that if you have angle I over here and if you have equal angle drawn on the other side with the surface with the wavefronts, because these two angles are perfectly equal, we can very easily draw the reflected wavefronts without even bothering about the normal. So easier way to do this thing is that you take your protractor, and place your protractor right over here. Let's say I'm doing it for the first line. So let's say you place your protractor right over here. Let me use blue, only blue. And so that the 90-degree point is over here. You take a measurement for how much degree that is. Let's say that degree is coming to be, let's say 70. বুঝতেছো কি বলতেছি? এই হচ্ছে প্রোটেক্টরের পজিশন। প্রোটেক্টরের 90 ডিগ্রি পয়েন্টটাকে আমি মাঝখানে রাখছি। সো দিস ইজ দ্য অ্যাকচুয়ালি দ্য নর্মাল লাইন। পোলাবান। So I want you to measure how much angle this is. If you measure this angle to be 70 degree, rest assured the reflected wavefront on the left side would be also produce a 70 degree. So what I want you to do is to give a dot at the 70 degree mark on the other side. Do that and then draw a line from this incident point to that mark point like this. And then you can repeat this same process for all the other incident points for the wavefronts. Be careful to keep them parallel and equidistant, which is very, very difficult on a freehand drawing. And that's basically it. Now, for those of you who are having a bit of difficulty to understand how these are the reflected wavefronts, or let me show you. This is the incoming wave direction, green line falling onto the surface. So falling onto the surface. So I should get rid of the earlier line. Let's say this is falling onto the surface at this angle. The reflection is supposed to happen in this way. Have a look. This is the direction of the reflection, which is perfectly perpendicular on your reflected wavefronts. Now you can skip drawing these green lines and you can skip drawing the perpendicular lines if you want. You don't have to. You can simply measure the angles on either sides and use the same principle, that the incident angle is very much the same angle that the wavefront produces with the surface. If you know this thing, which is very much helpful to draw these wavefronts. Did you get my point? I basically flipped the figure to the left. এই ড্রয়িংটা কি বুঝা গেছে?
Yes, sir.
বাকি দুজন? No, sir. হ্যাঁ। Zaima, Wasima, did you just write me no? টাইম স্ট্যাম্প দেখায় না কেন? বুঝা গেছে? আচ্ছা, ওকে। Zain, I think it's also okay. আচ্ছা, আমি লাস্ট আরেকটা জিনিস দেখে আসছে ক্লাস ক্লোজ করে দিব, কারণ আগাম দিয়ে দিয়েছে। সেটা হচ্ছে রিফ্রেক্টিভ ইন্ডেক্সের ফর্মুলা দিয়ে কিভাবে কাজ করে। আর লেন্সের জন্য তোমাদেরকে আমি একটা ইন্টারেস্টিং জিনিস দেখাবো। আচ্ছা, দুটো জিনিস দেখাবো। তোমাদের রিফ্রেক্টিভ ইন্ডেক্সের ফর্মুলাটা এরকম না, n equals to sin I by sin r। এটা কি দেখছো আগে?
Yes, sir.
প্রবন্ধে যে ঝামেলাটা হয় সেটা হচ্ছে এই আই কোন অ্যাঙ্গেল থেকে নিব আর কোন অ্যাঙ্গেল থেকে নিব সেটা নিয়ে একটা প্রবলেম, এবং প্লাস এই ইকুয়েশনের একটা থার্ড পার্ট আছে, সেটা হচ্ছে স্পিড অফ লাইট দিয়ে স্পিড অফ লাইট ইন ওয়ান মিডিয়াম ডিভাইড বাই স্পিড অফ লাইট ইন সেকেন্ড মিডিয়াম, এটা নিয়ে ঝামেলা হয়। এটা আমি তোমাদেরকে ক্লিয়ার করে দিচ্ছি। টিপিক্যালি দ্য ওয়ে আই অলওয়েজ টিচ দিস ইকুয়েশন টু দ্য কিডস ইজ দিস ওয়ে। Try to remember this very simple figure. Here we have air, here we have glass or water, whatever you can remember easily. There is a normal. Try to remember the shape of this figure. It helps. Let's say a piece of light ray is entering in from the air medium and is entering into the glass medium. So since it is going from lighter to denser medium, it is bending towards the normal. So let's say this is the incident angle I, this is the reflection angle X, R. For the sake of not confusing, I'm not going to write these angles as I and R. I'm going to write these angles as X and Y. Let's say this is angle X, this is angle Y. You might wonder, why am I writing X and Y? I have a reason. Whenever the light ray is traveling from air into glass, the refractive index would be given for glass. So refractive index হয় যে মিডিয়ামে লাইট রে এন্ট্রি করে সেই মিডিয়ামে typically, but it's not always true. I'll tell you why it's not always true, because different figures can be manipulated differently to give you different results as per your wish and requirement. So you are the person who has all the authority here. Let me show you what, let me just write this down. Refractive index of glass would be given by sin X by sin Y. And if we have the speed of light over here, let's say this is the speed of light in air, CA, this is the speed of glass, air, the speed of light in glass, let's say CG. You are using C. C is the typically physics symbol for speed of light. For different two medium, we're using two different subscripts. Then that refractive index can be also given by CA by CG. Now, this is a understandable formula. The easier way to remember this thing is that the refractive index, the medium for which you're trying to measure the refractive index, every property of that medium should go on the denominator side. This is the easier way to remember and not to mess up the formula. Have a look. If you're trying to measure the refractive index of the glass medium এর ভেতরে অ্যাঙ্গেলটার নাম কি? Y. That goes on the denominator side. Glass medium এর ভেতরে speed of light হচ্ছে CG. That goes on the denominator side. Using this exact same figure, you can do the other way around. I'll tell you why you can do the other way around. Let's say this figure was achieved by placing a piece of laser light over here. So this is a laser light source which was sending a green laser that could pass through this pathway. It is very much possible that we can choose that same exact laser pointer and bring it into the glass medium and place it right over here and aim the light in the upward direction. In that case, this light is going to follow this exact same pathway like this. Am I correct? Poloman?
Yes, sir.
ঠিক আছে। সো বেসিকলি আমাকে যদি এই সেকেন্ডারি সিনারিওর ফিগারটা দেওয়া নাও থাকে, তাও কিন্তু এটা ফার্স্ট ফিগার থেকে জাজ করা পসিবল। ইফ আই অনলি হ্যাভ দ্য ফার্স্ট সেট অফ ফিগার্স গিভেন, ইট মিনস দ্যাট লাইট ইজ এন্টারিং ফ্রম এয়ার টু গ্লাস, তাও কিন্তু আমার রিভার্স প্যাথওয়েটা বাই ডিফল্ট অ্যাচিভেবল, which means from that exact figure, whether the opposite directional arrows are given or not, I could also write the refractive index of air can be given by sin y by sin x, which is also equals to speed of air in at the bottom, speed of glass at the top. So যে মিডিয়ামে রিফ্রেক্টিভ বের করতেছি সেই মিডিয়ামের সব প্রপার্টিগুলো যাচ্ছে কোথায়? ডিনোমিনেটর সাইডে। এই জিনিসটা বোঝা যাচ্ছে কিনা? Take a good look at this one. Does it make sense?
Yes, sir.
ঠিক আছে, এখন আরেকটা জিনিস হচ্ছে যে যদি রিফ্রেক্টিভ ইন্ডেক্সের ভ্যালু মনে করো এখানে তুমি দেখছো যে এক্স অ্যাঙ্গেলটা বড় আর ওয়াই অ্যাঙ্গেলটা ছোট, তার মানে অবভিয়াসলি এই রেশিওটার ভ্যালু কি হবে? একের থেকে বড় হবে না ছোট হবে? Between sin x and sin y, which one should have a larger value? Obviously sin x will have a larger value because x is longer, bigger acute angle. So the total value of this ratio should be bigger than 1. Having a ratio bigger than 1 means glass is denser / slower. Vice versa, this ratio should be less than 1. Acha, whenever I say glass is a slower medium, what do you understand by this? That glass moves slowly or wave through glass moves slowly? What do you understand? I'll ask it again. Whenever I say the glass is a slower medium, what do you mean by it? That glass moves slowly or the wave through the glass moves slowly?
The wave through the glass.
Wave through the glass moves slowly, exactly. Slower medium doesn't mean that that thing itself is moving, so don't get the wrong idea. Coming back, the refractive index of air is less than 1. This basically means that air is lighter or air is faster than the other medium, in this case which is glass. So that's the whole idea of the refractive index map. You can have a lot of figures, you can have a lot of different angles given, but sin I by sin r helps us pretty well for the definition part. But if you're trying to get an universal expression of the formula, this is something that will never fail you, that whatever the medium's refractive index that you're trying to handle, that medium's properties goes at the bottom. So if you're trying to handle the refractive index of glass, everything relevant to glass goes at the bottom. If it's speed by speed goes at the bottom. If it is angle by angle, sin angle by sin angle, it goes at the bottom. এটা কি মনে থাকবে? এই জিনিসটা মনে রাখলে তোমাদের রিফ্রেক্টিভ ইন্ডেক্সে ম্যাথসে কোনো ভুল হবে না, and I guarantee you কোনো ভুল হবে না। Last thing, yes, this is amazing. I'll give this link to you. I'm not going to show much things from here. I'm going to give this link to you, and I want you to do some random stuff from this using this simulation, whatever you want to do, and then we'll pick up the lecture in next class, inshallah. Other group koi? I want you guys to access this link. আচ্ছা, আমি দেখাচ্ছি এই লিংকটা আমি তোমাদেরকে কেন দেখাইতেছি। This is a convex lens. এখানে ওরা অনেক কিছু দিয়ে দিয়েছে। এটা হচ্ছে distance of the object 10, distance of the height of the object 3. So each of these blocks are considered as one block. Magnification is minus 0.67. Minus দিছে কারণ হচ্ছে ইমেজ হচ্ছে ইনভার্টেড। 0.67 মানে হচ্ছে less than 1 মানে হচ্ছে অলটুগেদার আমাদের ইমেজটা সাইজ অবজেক্টের থেকে ছোট। এখানে ফোকাল লেন্থ দেওয়া আছে 4 ইউনিট। এখন একটা জিনিস খেয়াল করো, এখানে আমরা অনেক কিছু চেঞ্জ করতে পারবো চাইলেই। এই যে দেখো, we can do a lot of things. এবং এখান থেকে আমি তোমাদেরকে অনেকগুলো ডিফারেন্ট ফিগার পড়াই দিচ্ছি। মনে করো এই অবজেক্টটা ইনফাইনাইট ডিস্টেন্সে আছে। সো ইনফাইনাইট ডিস্টেন্স অ্যাকচুয়ালি থাকা পসিবল না। আচ্ছা, ইনফাইনাইট ডিস্টেন্সে যদি থাকে তখন যে জিনিসটা হবে, আচ্ছা ইনফাইনাইট ডিস্টেন্স আগে আপাতত বাদ, ইনফাইনাইট ডিস্টেন্স পরে পড়াচ্ছি। তোমাদের মোস্ট কমনলি যে প্রবলেমটা হয় সেটা হচ্ছে অবজেক্টের পজিশনের উপর বেস করে আমাদের ইমেজ পজিশনগুলো ঝামেলা করে। এইটা নো আচ্ছা, এটা দিয়ে দেখাই। এখানে একটা জিনিস খেয়াল করো, আমাদের ইমেজ প্রোডাকশন গুলো হওয়ার জন্য স্পেসিফিক কিছু জাজমেন্ট পয়েন্ট আছে। একটা পয়েন্ট হচ্ছে এফ, একটা পয়েন্ট হচ্ছে 2f। এখানে লেন্স থেকে আমাদের এফ হচ্ছে 4, 2f হচ্ছে 8। অনেকগুলো ডিফারেন্ট ডিফারেন্ট পজিশন নিয়ে আমরা কাজ করি। একটা পজিশন হচ্ছে ইফ দ্য অবজেক্ট ইজ আউটসাইড 2f, হ্যাভ আ লুক, দিস ইজ ফোকাস। সো লেন্স থেকে আমাদের ফোকাস পর্যন্ত হচ্ছে এফ, আর এরপর ফোকাস থেকে আরো একটু দূরে ইকুয়াল দূর, সো দিস ইজ আওয়ার 2f পয়েন্ট। সো ট্রাই টু আন্ডারস্ট্যান্ড। So in this case, image characteristics is real image inverted hi is less than ho, if is greater than di. আচ্ছা, এই জিনিসগুলো পরে বলতেছি। We're having a convex lens. Distance of the object is greater than 2f. Greater than 2f মানে হচ্ছে object 2f এর বাইরে আছে। Have a look, the image is between 4f and 2f. ইমেজ হচ্ছে 4 এবং 8 এর মধ্যে। আমি যত এই অবজেক্টটাকে কাছে আনবো, দেখো ইমেজটা আস্তে আস্তে বের হয়ে যাচ্ছে, খেয়াল করো। আমি অবজেক্টকে যত দূরে নিচ্ছি, ইমেজ লেন্সের কাছে আসতেছে, আর অবজেক্টকে যত লেন্সের কাছে নিচ্ছি, ইমেজটা আস্তে আস্তে দূরে যাচ্ছে। ডু ইউ সি দ্যাট? এই জিনিসটাকে বুঝো। Bringing the object closer makes the image go further and vice versa. Interesting point হচ্ছে, whenever I'm going to place the object at exactly 2f, so 8 is the 2f, do equals to 2f, the image will be also produced at exactly 2f. This is one of our terminal point. Object যদি এর বাইরে প্লেস করি, ইমেজটা ঢুকে যাবে, and whenever object is image is closer, it is definitely smaller. দেখো ম্যাগনিফিকেশন হয়ে গেছে 0.8। আমি যত দূরে নিব, আমার ইমেজ আরো ছোট হতে থাকবে। This is the position, this is the sweet spot where object distance is at 2f, that image will be exactly of the same size. The moment I enter into this position, image is gonna slowly start to get out. So if I place the object inside 2f, distance of the object is inside 2f, so distance of the object is between f and 2f, then the image has gone out of 2f. দেখো এই এটার বাইরে চলে গেছে। The further close I bring in, the more it moves out, the more it moves out, the more it moves out. If I place it in the focus, then the image would be not created because the rays will become parallel. However, this is not in your syllabus. They have deducted this from syllabus for reasons unknown. But if we place the object inside the focus, then we can have virtual image. These two rays are divergent, so they are not going to meet on the right side. So we could pull them backwards to get a hypothetical crossing over here, which gives us this position. So that's also possible. The point that I'm trying to make, bringing the object closer will make the image go further away. So what is happening, as we are bringing the object closer, the image is getting further. At 2f point of the object, image is exactly at 2f on the other side. If we enter the lens inside the 2f, the image is getting further out. And if we get at focus, the image is not created because the rays are perfectly parallel. If I move in further, then we can have virtual image which will be produced behind the lens because the reflected rays will become divergent, so that they would not cross on the right side, they will only cross on the left side. Now, where do all these things come from? What are the three different rays that we use to draw the lens? এই জিনিসগুলো আমি নেক্সট ক্লাসে বলবো। আমি জাস্ট তোমাদেরকে এই অ্যানিমেশনটা দেখাইলাম এটা বোঝার জন্য। This will help you to understand that the positioning information for the lens figures. আর লেন্সের ফিগার কিভাবে খুব ইজিলি আঁকতে হয় সেটা আমি তোমাদের নেক্সট ক্লাসে দেখাবো। আজকে এই পর্যন্ত থাক, ঠিক আছে? বলবান? আচ্ছা, থ্যাংক ইউ। আমি একটু পরে লেকচারটা আপ করে দিচ্ছি, আর তোমাদের এটা শুধু আপনার প্রাইভেট ভিডিও, আর তোমাদের মেসেঞ্জার গ্রুপে, মাস্টারমাইন্ড গ্রুপে আমি লিংকও দিয়ে দিচ্ছি। আল্লাহ হাফিজ।
Yes.